So let's begin part 2 of this lecture by looking at the temperature dependence of the equilibrium constant. If you recall from a previous slide in part 1, we established that at equilibrium, deltaG equals 0, and thus the standard deltaG can be equated to minus RT ln of K, where K is the equilibrium constant. We can expand this equation by substituting deltaH minus T delta S for deltaG in this equation here, and that's all I've done between starting here and here. Now let's do some rearranging. I'm going to bring RT ln of K over on the left side and bring deltaH minus T delta S over to the right side. Then if we divide both sides by RT, we'd have ln of K equals minus deltaH plus T delta S over RT. And then I'm going to isolate the 1 over T term here. So this expression in yellow is equivalent to this expression that we just left here. So we have the natural log of the equilibrium constant equals minus delta H over R times 1 over T plus delta S over R. Now this equation looks strangely like the equation of a straight line. We're not going to make that graph at the moment, but what we are going to do is rewrite this equation labeling K, K1, and T, T1. So in essence, we're saying, let's suppose a reaction has an equilibrium constant K1 at temperature T1. So if we rewrite this equation in the yellow box here, with those labels, we have ln of K1 at T1. And then suppose this same reaction has a different equilibrium constant, K2, at a different temperature, T2. The equation describing that situation, of course, would be ln of K2 equal to everything on the right side here with the temperature labeled T2. Now, we can actually subtract the equation involving ln of K1 from the equation involving ln of K2. So ln of K2, represented by this expression, minus ln of K1, represented by this expression. If we get rid of the brackets here, we'd have the first term written right here, and then we have minus a minus, so we have plus delta H over R times 1 over T1, and minus times this plus would be minus delta S over R. The convenient thing now is that these two terms involving delta S cancel out, and what we're left with is ln of K2 minus ln of K1, which can be rewritten in this form, equals minus delta H over R times 1 over T2 plus delta H over R times 1 over T1, and all of this can be rewritten as minus delta H over R times a quantity 1 over T2 minus 1 over T1. So finally here we have an equation with K2 at T2, K1 at T1. In this green box, this is actually called the Van't Hoff equation. You remember Van't Hoff from the Van't Hoff factor I. Well, this equation is also named after Van't Hoff. The nice thing about this equation, by the way here, delta H is in kilojoules per mole. R is the gas constant in energy units using kilojoules. And of course, T1 and T2 are in Kelvin. So again, the nice thing about this equation is that if you know the equilibrium constant K1 at temperature T1, and you know the sign and the magnitude of delta H, meaning how endothermic or exothermic the forward reaction is, you can predict the effect of changing the temperature on the value of the equilibrium constant. Let's see how we can do that. Let's recall for a second from a previous module that we said that an increase in temperature shifts an equilibrium in the endothermic or heat absorbing direction, and a decrease in temperature shifts the equilibrium in the exothermic or heat releasing direction. We came to this conclusion basically by invoking LeChâtelier's principle. We can show this in a little more quantitative fashion using the Van Hoff equation, which I've reproduced here. Let's use as an example the Haber process, which, as you recall, is a production of ammonia from nitrogen and hydrogen. This has a Kc value that's fairly small at a fairly high temperature, 500 degrees C, and it's an exothermic reaction written left to right. deltaH equals minus 92.4 kilojoules per mole. Now, we previously concluded from module 4 that decreasing the temperature would actually increase the yield of ammonia. Well, why is that? Well, remember, this is an exothermic reaction written left to right. If we decrease the temperature, the equilibrium will shift in the direction to offset that decrease in temperature. So it would shift in the direction that produces heat, and that would be in the exothermic direction, which would be left to right. So we'd predict way back in module 4 that if we drop the temperature, this equilibrium will become more product favored and our yield of ammonia will go up. Well, let's see if we can actually calculate a change in equilibrium constant. Well, if K1 is 0.058 at 773 K, now remember in the Van Hoff equation we have to use temperature in K, so I've converted 500 degrees C to K. We're asking what would this Van Hoff equation predict that the new equilibrium constant K2 would be at a lower temperature, and let's say 455 K, which is definitely lower than 773 K. So we have K1 of 0.058 at a T1 of 773 K. We have a K2 that we're trying to find at a lower temperature, T2, 455 K, and we know the delta H for this reaction is minus 92.4 kilojoules per mole. If we substitute these numbers into the Van Hoff equation, it would look like this. So our known K is K1, it's down here. Our unknown K is K2. And we put in minus 92.4 for delta H, so we'd have minus a minus 92.4. R here is 0.008314. And now we just solve for K2. Oh, and I forgot to mention, of course, this is obvious, but for T2 we put in 455K, and for T1 we put in 773K. So now we just solve for K2. Well, here's our equation from the previous slide. Kilojoules per mole cancel. And if you take the result of minus a minus 92.4 divided by 0.008314 and carry the units down, you get 1.111 times 10 to the fourth K. This K would end up on top. And I'm carrying one extra digit here. If you're careful with your calculator and use enough parentheses, you can figure out what this term is. Here I actually worked out 1 over 455 equals this number, be K to the minus 1 because K is on the bottom here. 1 over 773 is this number. So we take the result of this subtraction and multiply it by this number, and we get 10.04. So we have ln of K2 over 0.058 equals 10.04. We then remember from our properties of logarithms that the log of a ratio is equal to the log of the top number minus the log of the bottom number. Well, the log of the bottom number here, the natural log, is minus 2.847. So if we substitute that in there, we have ln of K2 minus a minus 2.847, which looks like ln of K2 plus 2.847 equal to 10.04. So ln of K2 equals 7.193. We take the exponential of both sides, which would leave K2 on the left, e to the 7.193. We write out as 1.3 times 10 to the third. So remember, the equilibrium constant at the higher temperature was 0.058. We lower the temperature and the equilibrium constant goes up to around 1300. So decreasing the temperature from 773K to 455 resulted in an increase in the equilibrium constant for this reaction from 0.058 to around 1300. So lowering the temperature does indeed favor the right side of the equation, the products. The decrease in temperature shifted the reaction in the exothermic reaction. So the Van Hoff equation does indeed make the same prediction as LeChâtelier's principle from Module 4. The advantage of the Van Hoff equation, of course, is the ability to actually calculate a number for the new equilibrium constant at the new temperature. Well, let's finish up this part 2 of this lecture by briefly covering a couple other things that might be of interest. One of the things that comes up in chemistry and in biochemistry is how do you drive a non-spontaneous reaction? Well, there's all sorts of ways that we can disturb and kind of manipulate the conditions to get a reaction to go. But one way to do it is what's called reaction coupling. And what this means is that you actually couple or combine a non-spontaneous reaction with a spontaneous reaction to try to get an overall reaction that goes forward, left to right, in the way you want. Here's an interesting example. Not every reaction that goes on in living systems is spontaneous. So for example, in human metabolism, the conversion of glutamic acid to glutamine is not spontaneous. This is something that needs to happen, and the deltaG for this reaction is plus 14 kilojoules per mole at room temperature. Well, that's a problem. How would we get this reaction to go? Well, if you recall from high school biology courses, the energy currency of cells is the spontaneous hydrolysis of adenosine triphosphate, ATP, to adenosine diphosphate, ADP. The reaction can be written as this. So we have ATP plus water going to ADP plus the phosphate group that's split off. The deltaG for this reaction is fairly negative, so this is a fairly spontaneous reaction. And by the way, this doesn't look balanced because I'm just using symbols for ATP instead of structures. If these two reactions are added together or coupled, one can see how the glutamic acid to glutamine conversion can be made spontaneous. So we're going to just do this on paper and show it mathematically, but chemically this does occur. So we have the glutamic acid plus ammonia going to glutamine plus water reaction with an unfavorable deltaG. We have the ATP going to ADP reaction with a very favorable deltaG. If I literally add these two reactions together, the water molecules cancel out because there's one on the left of the arrow here and one on the right. This should be a familiar process by now, adding reactions together. What we see is glutamic acid plus ammonia in the presence of ATP can produce glutamine, a phosphate group, and ADP. If we add these two reactions together, we simply add together the deltaGs And the overall deltaG, which I'm calling deltaG net here, for this overall process is now negative. So the conversion of glutamic acid to glutamine was made spontaneous by coupling the reaction to the spontaneous hydrolysis of ADP. Now, one more thing before we leave this lecture. It's not uncommon for general chemistry textbooks to make an attempt at explaining the origin of the word free in free energy. Now, as noted on the title on this slide, the sign and magnitude of deltaG for a reaction is related to the sign and magnitude of what's called the maximum useful work available from a spontaneous reaction, or it could be thought of as the minimum work required to get a spontaneous reaction to go forward. So what I've done here is I've added the superscript useful and reformulated this relationship below that basically says that the free energy change for a reaction is equal to the maximum useful work that we think we can get out of a reaction, or that can be gotten from a reaction, or it's the minimum work necessary to make a non-spontaneous reaction go. Well, an important caveat here is that this relationship is strictly valid only when the temperature and pressure are held constant during the reaction, and that's not an uncommon occurrence. So let's look at the sign conventions here, keeping in mind that in the past we viewed work done from the perspective of the system. So if deltaG for a reaction or a system is negative, of course the reaction is spontaneous and capable of performing work on the surroundings. Therefore, work would have a minus sign. System is losing internal energy as work. So again, if deltaG is negative, the useful work that reaction can do would have a negative sign, because the reaction would be doing work on its surroundings, and so W would have a minus sign. If deltaG for a reaction is positive, so if deltaG is positive here, then this work term is positive. The reaction is non-spontaneous and work must be performed on the reaction to get it to move forward. Therefore, work would have a positive sign because the system would be gaining internal energy as work. Now we could use the principles previously presented to derive this equation, but in all honesty, it's not clear that this would be terribly useful at this point, and you probably want to end this lecture and get this module over with. So let's just leave the slide by stating the following. For a spontaneous reaction, the magnitude of the negative deltaG represents the theoretical maximum amount of energy that is free to do useful work on the surroundings. The rest of the energy produced by the reaction is simply lost as useless heat to the surroundings. Remember, a spontaneous reaction results in an increase in the entropy of the universe.